Hi, Astronomy. Mr. Janowski here. This is part 9 of the chapters 14 and 15 slides. So, in the last part, we learned about black holes, and they are the corpses of the higher high mass stars. So, 20 times the mass of the sun or greater. When those stars die, you end up with a black hole. And we learned a little bit about black hole anatomy and things like that, and some of the weird properties about black holes. This part is going to get even weirder. This is basically about the weirdest thing I know. So let's get started with that. So, what's the distance from which the escape velocity from the center of the black hole is equal to the speed of light? 3 times 10 to the 8th meters per second. That is called the Schwarzschild radius. So here's Carl Schwarzschild, and there's your formula for Schwarzschild radius. So where is all of the mass of a black hole? That is all located down at the singularity. So, yeah, right there at the core of the black hole. And what do we call the surface of the black hole? We call this the event horizon. And I have surface in scare quotes because, yeah, black holes, as we're going to find out in this part of the slides, are so very, very weird that even thinking about their volume and their surface and things like that, it gets weird, and it's problematic to think of them in our everyday kind of sense of these words. So, yeah, we'll get there. So, yeah, here again is your basic black hole anatomy. All of the mass is down there at the singularity. And if you go out one Schwarzschild radius in every direction, that describes a surface that is the event horizon. So, yeah, the escape velocity from those points at the event horizon, the escape velocity is equal to the speed of light. If you go a little bit further, your escape velocity is less than the speed of light, which means it's at least mathematically possible and physically possible to escape from out here. But if you were inside of the event horizon by any amount, then the escape velocity is greater than the speed of light. And because nothing with mass can move that fast, that means you're not escaping from there. So, yeah, that's what the event horizon is, at least for now. It's about to get weirder. So, the event horizon is the surface containing all of the volume of the black hole. But again, as we'll find out, even saying things like surface and volume gets weird. So, yeah. So, general relativity. Yeah, if you had physics 2, we talked about this at the beginning of the year when we did relativity. So, according to Einstein and his theory of general relativity, this is his greatest idea ever, gravity isn't a force at all. So, by the time Einstein came around, we had Newton's idea of universal gravitation, and that worked extremely well for more than 200 years and gave very accurate predictions. And yeah, it worked very well. But Einstein's great genius is he came along and he said, no, you're not actually thinking about gravity the right way. So, yeah, according to Einstein, gravity is not a force at all in three-dimensional space. Gravity is actually the curvature of four-dimensional space-time. So, in Einstein's understanding, mass curves four-dimensional space-time. So, the more mass you have, the more space-time is curved, and there's lots of evidence for that. So, if we look at this picture up here, you can see three different masses, and this biggest mass here is curving the space-time the most. The middle one, not as much, and the lightest one is curving it just a little bit. And yeah, you can kind of see this in the GIF here. So, yeah, if you're into, physics and this weird stuff, you may have seen GIFs like this or images like this. So let me just briefly explain what's going on here. This is kind of an image like this is really an analogy. So the analogy here is it's showing you mass curving two-dimensional space. So think of this flat plane as two-dimensional space, and what the mass is doing is curving that two dimensions of space into a third dimension. Now, I can't show you three dimensions curving into a fourth dimension because I can't draw it and you can't visualize it. It's basically impossible because we pretty much live in a three-dimensional spatial world, three-spatial dimensional world. But yeah, so that's what this is. Images like this, they're always an analogy. So anyhow, yeah, the more mass you have, the more space-time is curved, and there is a lot of evidence of this. So yeah, a lot of evidence for the fact that mass curves four-dimensional space-time. So first, the idea that mass curves space. So we've had very direct evidence for this since 1919. So Einstein's general relativity, he published that idea in 1915. In 1919, there was an eclipse, and by that point, people knew a guy named Eddington, Arthur Eddington, did the actual measurements. But by that point, they knew that if Einstein were correct, then something as massive as the sun should be curving the space in the vicinity of the sun. So this is what is being shown in this picture. So ordinarily, you can't see the stars that are very near to the sun because the sun is so bright, and it's during the day you can't see them, but during an eclipse you can. So what's actually going on here is you've got a star way back here, and its light would pass fairly close to the sun or maybe even be blocked by the sun. But what happens is, because the sun is so massive and curves spacetime so much, that the light that's leaving this star gets curved as it goes around, and by the time it gets to Earth, it's following along this path indicated by the white line. So what that means is, from Earth, if you look out, you will see the star. It'll appear to be along this straight white line out here, even though measurements you've taken at other points of the year tell you that it should be here. You'll notice it way out here. Now, this is clearly, none of this is to scale, and the deflection is not nearly this much. It's actually very, very tiny and very hard to measure, especially in 1919, but they were able to do it. So yeah, this is mass curving space. Another example of this, so this smiley face is an example of what's called gravitational lensing. So what's going on here is you have, I don't know if these are elliptical galaxies in the foreground. I'm not exactly sure what the big mass is. Maybe it's this guy, maybe it's all three of them. But basically, light from more distant objects is traveling from behind, and when they pass these things are curving space so much that it's bending the light, and instead of showing up as like clear little points like these other galaxies do, it gets all smeared out. So yeah, it's a lot like, it's called gravitational lensing. It's a lot like looking through a very weird lens. So I mean, the neat thing in this picture is, yeah, this very strongly suggests a smiley face, two eyes. We even get a nose and a mouth. So it just happens that this example of gravitational lensing looks like a smiley face. So that's really cool. So yeah, we've had evidence for mass curving space since 1919. Now, mass also curves time, and this is really, really weird. But again, we have a lot of evidence for this. So time is going to run slower near massive objects. So, for example, in this picture here, this guy is down here in the valley. This guy's up here on the mountain. So the guy that's in the valley is closer to the mass of the center of the Earth than this guy up here on the mountain. So because the guy in the valley is closer to the mass of the Earth is curving time, and it's causing his clock to run slow. So if he looks at it, he's not going to think it's running slow because he's standing right next to it. He's experiencing time the exact same way as the clock is, but it's making it run a little bit slow. Whereas this guy that's up on the mountain, he is just a little bit further away from the center of the Earth and from all of the mass of the Earth. So his clock is going to run a little bit faster than this one. It's going to be less affected by the mass of the Earth because he's just a little bit further away. So if he looks at his clock, he's going to see it as running normally. If this guy looks at his own clock, he's going to see it running normally. But when this guy in the valley looks up at this clock on the mountain, he's going to say, no, that clock's running too fast. And this guy up here is going to look down and say that, no, that clock is running too slow. So you wouldn't be able to notice this. The effect is so slight that, yeah, you wouldn't see this. It is actually measurable, even on fairly small scales. You can take atomic clocks, get them in sync, and then leave one of them on the ground floor of a building, take another one up just a few stories, to the fifth or sixth story of the building, let both clocks run for a couple hours, and then when you bring them back together, you will see that they're no longer in sync. The one that stayed on the ground floor is going to have been made to run slower from all that stuff. And the one that went further away from the mass of the Earth would feel less of the effect of the mass of the Earth, and so that one would have run a little bit faster. So a very slight effect, but you can measure it. And one extremely important application when you're doing this is GPS satellites. So GPS, without going too far into it, basically works by having extremely accurate measurements of time. So all of the satellites have their own clocks, and they're comparing them to basically clocks on the Earth is kind of how it works. So the satellites are up in space, so they're further away from the mass of the Earth than the surface of the Earth is, and so they're feeling less of the Earth's effect. So their clocks are going to run a little bit faster compared to clocks on the Earth. And in order for GPS to work, they have to account for this general relativistic slowing of the clocks that are close to the Earth. Again, the ones up on the satellites are going to run a little bit faster compared to those down on Earth. So yeah, it's very, very weird. But this is great evidence for the fact that Einstein was correct about mass curving space and time. Is the fact that our GPS wouldn't work if we didn't account for this. If we didn't account for this, you would set up the whole GPS system and it would work pretty well for a couple of minutes, and then it would be hopelessly out of sync and it wouldn't be able to tell you where you were anymore. But of course, it works very well. So if you're falling into a black hole, if you're far enough away from the mass of the black hole, it's going to act just like any other massive object. So we had this idea in the last part. If you were to suddenly replace the sun with a black hole that had the mass of the sun, again, that's not going to happen. But if you were to do it from out here on Earth, the gravity would feel exactly the same. So the Earth would keep orbiting that one solar mass black hole exactly the same way that it orbited the sun, only no more light and heat, so suddenly it's going to get very dark and cold. The weird thing is if you're really close to the black hole, you're really close to a whole lot of mass, and that's going to curve space and time a lot, and things are going to get very weird. So the key point of this slide is if you're far enough away from the mass of the black hole, things are fairly normal. It's just regular gravity, and it works the way we're used to. If you get really close, that's when you start to get pretty bizarre effects going on. So if you're falling towards the black hole, so we're going to think of this from a couple different perspectives. So we're out here far from the black hole, and then we're going to fall in. So what you're going to experience as this object is you're going to keep speeding up because you're falling and you're getting closer to the mass, so gravity keeps acting stronger and stronger. So you're going to say that, no, I keep speeding up and speeding up. And yeah, eventually you would just cross the event horizon. So what happens when you get to the event horizon? We're not sure. There are different theories. This is an open topic in physics. So either nothing happens and you just cross the event horizon, and then eventually you get ripped apart by the tidal forces, and you get spaghettified and all that stuff happens. And so you die. But just a little bit after you cross the event horizon. The other idea is that for quantum mechanical reasons and the conservation of information and weird things that I personally don't really understand that well, some people say that the instant you cross the event horizon, you hit essentially some kind of firewall and you're instantly destroyed. So which one of these is correct? It's an open topic in physics. No one really knows which of these would happen. So now, same situation, only this time, instead of being the object that's falling in towards the black hole, we're going to stay outside of the black hole, and we're going to watch the object speed up. So what we would see is, first of all, the object is going to speed up because it's getting, gravity's pulling on it, so it's making it accelerate. It's speeding up as it falls towards the black hole. But then at a certain point, this curvature of space and time is going to kick in, and something strange is going to happen. Because of this massive curvature of especially time, we're going to see the object slow down. So it was, when it's way out here, it's falling in and it's speeding up, and it would keep accelerating, but at a certain point, general relativity kicks in, and the object would actually slow down and slow down and slow down until it would eventually stop, which I have an asterisk here, because it doesn't just actually freeze there, it gets confusing. It would keep slowing down, as if it were approaching a stop, and then it would get redder and redder, and dimmer due to gravitational time dilation, gravitational redshift, meaning the light that's leaving this thing, because it has to kind of fight against this gravity, it gets redshifted, and it would get dimmer and dimmer until eventually, you would think that it would stop, but really what happens is it just gets redshifted into infrared, then microwaves and radio waves until eventually you can't detect any of the light coming from it. But you don't actually see it there stopped, is the point of this. So yeah, here's the weird paradox: is according to the outside observer that's watching something fall in, it never actually enters the black hole, which is very, very bizarre. Because from the perspective of the thing doing the falling in, yeah, it just zips in, going faster and faster, and it crosses the event horizon, and now it's in the black hole. But if you're watching this happen to something else, you're going to say, no, it never actually gets there. It speeds up for a while, and then it slows down, and then it kind of crawls to a stop and gets redshifted until you can't see it anymore. So, yeah, the very weird thing about this is the idea of the event horizon. So, to understand what a black hole actually is you have to break this very just kind of obvious and conception you have, preconception, that a black hole is somehow a region of space that's up there and has a volume and has a surface and all of these things. The problem is this gets so extreme that you can't even think of it as a region of three-dimensional space anymore. You have to think of it as events in four-dimensional space-time. So, yeah, in this context, what the event horizon is, it's the sum of all the events that the outside observer never gets to see. That event has been deleted from the perspective of an outside observer. So the event in this case is the object crossing the event horizon. So if you are that object, that just happens. And if you're outside of the black hole and you're watching this, you never ever see that event happen. That event is deleted from your space-time. So I'm sorry, it's deleted from your timeline, from your reality, from your experience of time and space. So that event never happens, as if that event were over the horizon, and you just can't ever see it. So I highly recommend watching this video. Excuse me. Yeah, if you're in physics too, we watched this video. We discussed this earlier at the beginning of the year. But yeah, this is such a crazy idea that it's worth watching again and seeing if it makes more sense. And spoiler alert, it's probably not going to make more sense. I've watched this video many times. I've thought about this for hours and hours. And yeah, it just doesn't make sense. It's really weird. But he goes over the thing I just explained. How basically the event of, in this situation, he's going to have a monkey fall from his position into the black hole, and he and the monkey are going to very much disagree about what actually happens. The monkey is going to say that, yeah, it crosses the edge, and now it's in the black hole, and it's gone forever, and can never get out, and can never send a signal out about what happens. But yeah, the monkey would definitely think it crossed the edge of the black hole. Whereas from the perspective of everyone out here, the host of this episode is named Gabe, he's going to say, no, the monkey never actually gets there. It zips towards it, going faster and faster, and then starts slowing down. And then it just freezes there at the end, gets redshifted away, and disappears. So, yeah, the title of this video, do events inside of black holes happen? You can't say. It's really, really weird. This is at the edge of our understanding of physics and astronomy and all this stuff. So neat stuff. So yeah, again, this is what I just said. According to the monkey, he's going to zip in. He's going to speed up the whole time and cross the edge of the black hole, and then eventually the monkey will get ripped apart by tidal forces. But according to Gabe and all of the observers outside of this, including we've got the little ponies in orbit around the black hole, everyone's going to say that the monkey never actually crosses the event horizon. So yeah, it's weird. This is the idea that a black hole, again, is not a region of three-dimensional space that has a volume. It is the sum of all of the events in four-dimensional space-time that have gone missing according to all outside observers. So yeah, ideas of causality and time and space, it all gets really, really weird in this. So to review, I have just one question. Do events inside of black holes happen? And the answer is, I don't know. And people smarter than me don't know. This is really not known. Black holes are so very bizarre that we don't understand this stuff. It's just craziness. So yeah, obviously I'll put a link to that video. Watch that video if you find this stuff interesting. And yeah, hopefully you found this part of the slides interesting.